Okay, let's try a few questions today, right? System of equations, but not the usual problems, right? But let's try to compute x minus y here whenever we have these two values. Right? Really, I think you can easily understand it's not possible to compute x and y, I think. Actually, we can, but that's very difficult. So the most important thing is computing x minus y. That's what we need. So I'm going to use some known factoring method. We know that difference of two squares, p squared minus q squared equals to p minus q times p plus q. So I'm going to use this for x squared minus y squared. Because there is a reason. Since we want to compute the value of x minus y, right, we need a relationship between these three: x squared minus y squared, x plus y, and x plus y. Here's the relationship. It's a known concept for factoring quadratics. So therefore, we can apply this. And also remember, x squared minus y squared and x minus y whole thing squared, those two are completely two different things. So in this case, we do have the value of x squared minus y squared, that is 36. And we need x minus y. Then x plus y equals to 12. So I can substitute 12 here. That's multiplication between x minus y and x plus y. So here we have that multiplication symbol. Now, can you solve this one for x minus 1? It's like, think about that x minus y is a single term. Consider that entire term as a single term now, because we are not going to compute x and y separately, right? So I think here we have a situation like this. 36 equals m times 12, like that. So to compute m, you can divide both sides by 2. Right? So then m equals to 3. So in this case, m is x minus 5. So basically we are dividing both sides by 12. Right? If that's uncomfortable, you can use this. Just use a different symbol for x minus 5. That's all. Right? So then 12 and 12 can cancel. So x minus y equals to 3. That's the answer. Right? Sometimes there can be questions with these two values, x squared minus y squared and x minus y. Then you can compute x plus 1. Right? So that's the concept. So then we can try a question like this. Quite similar. For this, to solve this problem, I would like to mention one formula, that is a to the power of 3 minus b to the power of 3. You might have seen this. You can factorize this. Again, a minus b, a squared plus b squared plus ab. So you can use this formula for this case. So again, you can't really compute x and y and substitute x and y for this expression. That's too difficult. Really difficult. Nearly, no, we can, but very difficult. So in this case, I'm going to apply this formula for x cube minus y cube. X acts like A, B acts like B, B acts like Y acts like B, right? Then this part that is just 54, then x minus y equals to 4. So we can replace. Don't worry about this entire part. Yeah, there are 3 terms, but if you want to, you can consider that whole thing as a single term. That's exactly what that's what I'm going to do here. Because we need that quantity. So to get that, you can divide both sides by 4. I think that's the answer. It's not possible. We won't be able to get a integer, but that's not a problem. 54 over 4, you can simplify that. 27 over 2, 13 and 1 over 2. That's fine. That's not a problem. We are not expecting a whole number. So that's the answer. You can remember this formula. Sometimes you can apply that. Once again, identifying this entire thing as a one term is quite important. Then this problem. Again, I think now there is a difference. For this problem, now we need x squared plus y squared. Here we have x plus y squared and xy. The question that you should ask from yourself is, what's the connection between these 3 quantities? Yeah. So x plus y squared. So maybe let me write a plus b squared. That is a squared plus b squared plus 2ab. If that is confusing, you can multiply a plus b by a plus b. You will get the same answer because that's the meaning of a plus b squared. Now, if I use x and y instead of a and b, I'll get something like this. And then I think we have a relationship between these 3 quantities. X plus y squared, x plus y entire thing squared. Then xy, here we have xy. Then x squared plus y squared. So there are 3 quantities. We do know the value of 2 quantities. Basically these 2. We do have the value of x plus y squared, and also xy. 2 is not a problem. 2 is not a problem because we are going to multiply xy by 2. We can do that. This part, again, this entire term, one thing, right? That's what we need. I think we can compute that part because we do have x plus y squared and xy. So let's substitute these values. 25 here. X squared plus y squared, that's the unknown value. Unknown value plus 2 times this xy equals to 6 because there's a multiplication sign between 2 and xy, right? So that multiplication sign, yeah, I put that. Then 25 equals to x squared plus y squared plus 12. Now, once again, it's like it's a linear equation. Why? Because I can consider this whole thing as a single term, like 25 equals n plus 12. Then you can move 12 to the other side. That's the idea. Let me move 12 to the other side. That is x squared plus y squared. That is 13. Right. And also sometimes for some problems, you can use that a minus b whole thing squared, that expansion according to the problem. But I think now you will be able to understand the concept behind computing these values, right? Not just single variables, but quantities with multiple variables. Still, we can compute them. Because computing x and y can be very difficult here, and that's not the requirement. And as I mentioned, this problem is quite similar to the previous one. The only difference is we should use x minus y whole thing squared. X squared plus y squared. Okay, let me write that formula. A squared plus b squared. Then the sign is different, minus 2ab. So I'm applying that formula here for x and y. So that is x squared plus y squared minus 2xy. Quite similar. This part equals to 9. Here 17 minus 2 times xy. I would like to express that one inside a bracket. Now we need that value. Again, it's like 9 equals 17 minus 2w. A situation like this. Solve this one like a linear equation. So maybe you can move this minus 2w to this side and 9 to the other side. Sign will change. 2w equals to 17 minus 9. W equals 4. After practicing this concept for few problems, you can apply that concept even without using a different symbol like W, right? So I really encourage you to apply that concept without using a different symbol, right? So like this, I'm going to move this minus 2xy to the other side. If that is confusing, you can keep that, no worries. You can move 17 to the other side. 9 minus 17. Minus 2 times xy. Minus 8. Minus 2 times xy. Now I think we can divide both sides by minus 2 because we need xy, not xoy, right? We need that entire thing. So divide both sides by minus 2. That's the xy value, 4. Right? Okay, very important concept. Yeah. So you can apply these concepts for different problems. The key idea is identifying, recognizing the correct relationship that you can use for any given problem, right? So let me show you. Now we did discuss these 4 questions. but we use different formulas for all of these problems, different formulas. For this one, we use difference of two squares. Maybe you can write these formulas again. And for this one, difference of two cubes. For that one, we use a different formula like this. And also be careful, there is a large major difference between x cube minus y cube and x minus y to the power of whole thing, to the power of 3. That's a clear difference. So be careful. And here also this is x plus y squared. Here we use that. And here x minus y squared. So those formulas quite helpful. But identifying the correct formula, very, very important for these problems. Right. Thank you very much. Right. So let's try a few substitution rule problems. To integrate, we use substitution rule, right? Because some integrals is not straightforward. So then we use that substitution rule, particularly for a problem like this, natural log. Now here, key here is identifying the correct substitution. But how would you identify the correct substitution? That's the main, most important part. Right? In this case, let me do something like this. For this integral, let's say I equals, I would like to express this integral like this. Natural log of x times 1 over x dx. Then, if you observe carefully, now this 1 over x and natural log of x, there is a relationship between those two, right? Because the derivative of natural log of x is 1 over x. Let me write that here. Hence, if I want to, I can write this integral like this. Natural log of x times the derivative of natural log of x dx. I just replaced this part by this, because both equal. Right? Now observe this pattern, very, very important. Now, after creating a form like this, or after identifying a form like this, you can easily choose the appropriate substitution. That is basically this part, natural log of x. Because here we have the derivative. Hence, now I am going to write my substitution, u equal natural log of x. So we use substitution for a reason, to simplify the integral, but we should convert the entire integral into a new variable. Now that is u. So we should convert dx to du. So to do that, we can differentiate both sides of this u equals ln x, natural log of x substitution with respect to x. Some people write like this, 1 over x, or someone can differentiate like this. That's also correct. Right? After that, I think you can easily identify du equals to 1 over x dx. Hence, for focus on this part, this is the integral that we are going to integrate. Yeah, of course, that integral equals to this. But we did this to identify the correct substitution. After identifying that, we can use this original integral. Right? So my advice is creating a form like this helps us to find the correct substitution. Right? After that, we can use that U substitution for this yellow colored part. Right? That is basically natural log of x is u, 1 over x dx, that is basically du. So u du, we can easily differentiate, we can easily integrate u to the power of 1 plus 1, u squared over 2, plus c. Here u equals to natural log of x, whole thing squared over 2, plus c. That's the answer. Very important, identifying the correct substitution, because after that it's quite easy computing the integral. Right. Now the interesting thing here is, now after solving this problem with that exposure, you should be able to complete this question. Right? Let's say j equals to natural log of x whole thing squared. I like to express like 1 over x dx. Always try to express these integrals as a product. That way you can see things clearly. Right? Now again, observe this 1 over x part. That's the derivative of natural log of x. Right? In other words, I can deform that natural log of x squared into two functions, x to natural log of x, natural log of x to natural log of x to the power of 2. So this is the outer function. This is the inner function. More often we use a substitution for inner function, that is natural log of x. So, and you can confirm that by writing 1 over x as the derivative of natural log of x. Like this. This pattern is quite important. Then you can use that substitution, u equals natural log of x. Then we can easily integrate because du equals to 1 over x dx, very similar. Equal to u squared du. So j equals to this. We can integrate u to the power of 3 over 3 plus c, and u equals to natural log of x. That's the answer. Right? So observe this form. That's quite helpful. Creating that form, right? Then this part here, this part, this function, that's the substitution. After creating that form, you can easily identify the substitution. If you want to, let's try to differentiate this answer. Don't worry about C because the derivative of C is 0. So I'm going to differentiate natural log of x to the power of 3 over 3. You can take 1 over 3 out. Then I think we can apply chain rule because this is a composite function. Initially differentiate the outer function. For outer function, that is x to the power of 3. That's the outer function. That's a different topic, right? If you have doubts, I'll explain that later with a different video. Now, natural log of x to the power of 3, the outer function is x to the power of 3. So when you are differentiating the outer function, please fix this part, natural log of x, that one acts like x. For example, we initially differentiate x to the power of 3, but x is natural log of x. So like this, 3 natural log of x to the power of 3 minus 1. Then we move towards the inner part of the function, basically the inner function, that's natural log of x. Differentiate that one. Like this. Now 3 and 3 can cancel. Of course, we can simplify this slightly. Now, if you can observe these two, this part and this derivative, basically the same thing, right? So hence the derivative of this function equals to this. Hence the antiderivative of this answer is the original function that we did differentiate. So like this. Now I think if you think carefully, you can understand why did I create this form initially to identify the substitution, right? Okay. I'd always try to create that form. It's quite helpful. Right. You can try that for the previous program also. Try to differentiate this function. You will see this pattern, this part. You will be able to identify those patterns. That really helps. Instead of applying trial and error method, you can find substitution using this kind of a method because you can apply this for any problem. Yeah. Now this third one, again, I think we can try this one. A general case of previous two problems. To integrate this, again the same idea, 1 over x dx. So I would like to express like this. Now here, again, focus on this part, natural log of x to the power of n. The inner function is natural log of x. That's very important. Then here we have the derivative of the inner function. Right? Once again, that form, that's very important, that form. Then you can use a substitution. Afterwards, it's quite easy, I think. Right? Again, u equals natural log of x. I think you can continue that process. You will get something like this. Try this one as a practice problem. Then u to the power of n plus 1 over n plus 1. Actually, I should mention here, n should not equals to minus 1. There is a reason. Because we can't apply power rule of integration when n equals to minus 1. Right? We can discuss n equals minus 1 case separately. Plus c. Then we can replace that our original variable natural log of x to the power of n plus 1 over n plus 1 plus c. That's the final answer. So when n equals to minus 1, that is natural log of x to the power of minus 1 over x. I can move natural log of x to the denominator to make that exponent positive. 1 over x natural log of x dx. I think once again, the same idea, we can apply that idea. 1 over natural log of x, 1 over x dx. This part, this is the key here actually. 1 over x. That's the derivative of the inner function. Maybe can be difficult to understand sometimes, but this is a composite function. The outer function is 1 over x. That's the outer function. If you want, I can draw that function. X2 natural log of x, that's the inner function. Then natural log of x to 1 over natural log of x. The outer function is basically 1 over x. Right? So we oftentimes we use substitution for the inner function. So our substitution should be u equals natural log of x by 1 over natural log of x. This is the derivative of natural log of x. Like this. Then we can, once again, that same pattern. Right? So you can use u equals natural log of x. Here. Then 1 over u du equals to 1 over x dx, hence du. But here we can't use power rule because n equals to minus 1 if I move that u to the numerator. Can't apply power rule of integration for this. But we can use natural log integration because we know that the antiderivative of 1 over x equals to natural log of x. Hence here, natural log of u plus c. We put that absolute value because natural log defined only for absolute value, only for positive values. Like this. Therefore, natural log of our substitution is natural log of x. So natural log of natural log of x. Right? Like this. Plus c. That's the answer. But the interesting thing is for all of these problems, I used the same substitution. Why? Because of one reason. You can identify that. That's great actually. Let me show you all the problems here. All of these problems, I used the same substitution, which is natural log of x, that's because of this x. You can try the fourth question actually. I'll explain that. Because this 1 over this x in the denominator is actually 1 over x. That's the derivative of the inner function. For that one, just one function. But here, the inner function, the derivative of the inner function. So that's the idea. I think you can try these two questions now using that idea. Try that, I'll explain in the next session. Okay, thank you very much.